No, you should call me out. I need to know those things. I need to correct them. Okay. So we need this. We got that. We need this. Probably not the right one. Okay. Too many things open. All right. This should be good. Okay. Yeah, even if all good. All right. So on Friday, we looked at a couple examples of related rates problems. I took a second after class and I put everything from this unit in Desmos. So let's kind of review a couple of the things we looked at. One of the questions that we had to answer, it was really the one where we were just doing the math. There really wasn't too much of a story problem behind it. But we were talking about a particle moving on some sort of weird curve. And I was talking to you guys how about dy dt and dx dt track the rate that you're moving left and right and the rate that you're moving up and down. If you remember, I was kind of saying like fast walking across the front of the room saying like I'm tracking that particle on the x-axis. But a good visual for that, because our job was to find dx dt at this specific point. But this picture kind of shows that idea. So I just kind of want to have a better visual for some of these. So I'm going to reset this. The particle is traveling on that weird curve. And if you can see, there's a dot on the x-axis and a dot on the y-axis. And that's the thing we're actually trying to find the speed of, or the velocity of. So dx dt represents how fast this red dot moves on the x-axis. dy dt represents how fast this blue dot moves on the y-axis. In BC Calc, there's actually a section where we talk about this stuff, and we learn how to figure out all three of the velocities: the velocity of the red dot, the velocity of the blue dot, and the velocity of the actual thing we're talking about, which is the purple dot. But that's a BC only topic. So you'll see that in college if you keep going with this stuff, but we won't do it. So anyway, so as that dot, the purple dot moves, dx dt and dy dt are the speeds of the red and blue dot individually. You can see that the blue dot ends up moving really, really fast as it goes through that weird bowl shape down at the bottom. But that is what we're doing. That's the idea of this lesson. The only other problem we solved was the problem with the circle. And I think that's a good one. I tried to visualize this, but sometimes speaking a visualization isn't the easiest thing in the world. This really gets to the idea of related rates. The question was, we have a circle that's expanding. So when I press play, my circle is going to expand. In this demonstration, I also decided to put kind of waypoints on the way. So every time the radius increased by 1, I put a little dotted circle there, okay? We wanted to figure out, so the way that problem was worded was that the radius was increasing at a constant rate. And anytime I'm working in Desmos, that's kind of how it works. If I make a slider and press the play button, that's going to move it at a constant rate. So I'll press play one more time and we'll watch that circle increase radius-wise at a constant rate, okay? When we wanted to figure out what rate the area was increasing at, we needed two things. We needed the constant rate of the radius, but we also needed to know where we are. And that's why I have these rings there. Look at this ring right here that I'm pointing to. This is the ring that represents how much more area there is from radius 1 to radius 2. There is, and I'm running my finger over it, this much area. Is that the same amount of increase in area when you're out here between 8 and 9? No. So, because that is just the way the physical world works. But that is why our formula, or both our formula and our question, kind of required the radius. Because even though the radius is increasing at a constant rate, the further out you are, the faster and faster the area is increasing. I tried to say that in words, but I think a visual kind of does a lot better with that. And again, that's kind of how these problems are written. They're written where one of the rates is constant, and we'll figure out anything else. It doesn't have to be that way, but for a math problem in a math class, anything more can be a little bit complicated. All right, so let's take a look at the problem we have to start with today. That is going to be example 4. Before we do that, some general things we want to talk about when we're solving these problems. in the end, you could probably spend 2 weeks on related rates. There are enough different types of problems in the book to almost make a whole class on it. But we're not going to do that. So when you're doing a related rates problem, a lot of times it's figuring things out. So this process, the first thing we should do, especially if it's a problem we've never seen before, we need to draw a picture of the situation. We'll show movement with arrows, and we're only going to label static variables. Okay, this is probably this first part, and this is something we didn't have to talk about in the other ones. We just kind of did the problems, but the more complicated they get, the more important this is. A static variable is something that isn't going to change. Okay, so it's, almost, the word variable is almost a bad name for it because variable means something that can change, but a static variable will never change. And a dynamic variable is something that is changing. When we're labeling a picture, we only want to label the static variables. That's important. Because when you go to take that derivative, we get to plug in the static variables before we take the derivative, which simplifies things. And if you plug any dynamic variables in before you take the derivative, you're going to get the wrong answer. What we're going to do, especially in our initial questions, is we're really going to translate the given information and tell what it is. Like we're, oh, that number in the problem, that's X, and we'll write X equals that number. Oh, that number in the problem, that's dr dt. So we're going to label that. And we can even, go a step further. If they're asking a question, what is the rate at which the area is changing? We can even write dA dt equals question mark to give us an idea of what we're solving for. Step 3, we need to use an equation. Any equation you've learned in all of your years of math, whether it be the Pythagorean theorem, whether it be the area formula, whether it be a volume formula for some shape, those are the formulas we use a lot of times in these problems. On the AP test, I think they try to give like standalone questions. So a lot of times if you see a related rates question, they do show up in FRQs. A lot of times it's nice for that particular question because they're giving you the equation and it's your job to just to take the derivative of it. We'll differentiate with respect to time. That's kind of what we were practicing on Friday. And then after you've differentiated, you should have all of the variables but one. So you plug all of the variables in but one, and then you solve for the missing variable. So the thing we do in math. Don't forget, we saw an example of this. I think this is the example we finished up with Friday. If you're missing something in the end, there may be some way to solve for it. Okay. So if you're going to plug in and you're like, oh, I need dA dt, but I don't have z over here. Well, did the original equation actually help? Could you have used that to figure out z? So we'll see that all as we're going along the way here. Let's take a look at our first problem that we're kind of going to do the whole problem solving steps, the whole set of problem solving steps for. A 13-foot ladder is leaning against a wall when it begins to slide down the wall at a rate of 2 feet per second. Implied in there is that is a constant rate of 2 feet per second. Let's draw a picture to model this situation. So we'll draw the picture first, then I'll bounce over to Desmos to show you what I drew in Desmos to kind of show this problem. We have a wall. We have a ladder leaning against that wall. Depends on my angle there. And we have the ground. A 13-foot ladder. Is the length of our ladder changing? No. So that is a static variable. So we can actually put a 13 on that. Okay. 2 feet per second is a rate. So we are going to label that with an arrow. That's the rate at which the ladder is going down the wall. So we will label that 2 feet per second. What rate is mine on all this?
Please excuse the interruption. At this time, all students taking the Keystone exam, please transition to your testing room. And this is a reminder that no electronic devices, purses, or backpacks are allowed in the testing room. Please put those in your locker first. Thank you.
Sometimes it's nice and it works this way. At what rate is the base of the ladder moving away from the wall when it is 5 feet from the wall? That's one more number we have to use, but is that 5 feet staying the same or is that going to change? That is going to change, yeah. So I'm not going to label anything on my picture with 5 feet. Okay. So here's our picture. Let's take a look at what I have in Desmos. This is probably the boring one of the group. There wasn't too much to draw here, but it's this one. That green line represents my ladder. I think I did a better job. If it's a 13-foot ladder and it's 5 feet from the base, I think it's going to be a lot steeper than I have it drawn in our picture. Hello. Lit. True. All right. Alrighty. The ladder is falling at a constant rate. Here's a question. Watch the base. Is the base moving out at a constant rate? There we go. No. Yes, especially at the end there, you can really see that dot at the bottom has slowed down significantly. So although the ladder is falling at a constant rate, that base does end up slowing down quite a bit. But that's what's happening there. And the question wants to know, kind of at my starting position here, where I had it started before. I'm going to get this back to there. Yep. At what rate are we moving at that specific moment in time where the base of the ladder is 5 feet? All right, so let's continue with the problem solving stuff here. We need to give these, kind of look at B and C together here for a minute. So we've got to give some variables to what we have in our picture. And then letter C, we want an equation. Anybody have an idea of what equation is going to help us relate all of the different lengths in our picture? What's that? Is there anything about area in our problem? No. It is the Pythagorean theorem. Because we know that we are 5 feet from the base of the wall, but do we know how tall the ladder is? Or sorry, I did say how tall the ladder is, but I mean, do we know how tall up the wall we are? It is, but that's the Pythagorean theorem that does that. Yeah, so it's the Pythagorean theorem that's going to help us in this one. So I'm going to use the letters. I'm going to steal the letters from Pythagorean theorem, and I'm going to label my wall A. I'm going to label my bottom B, and we'll call the ladder the hypotenuse C equals 13 feet. Okay. So we will say that A equals 13 feet. B equals 5 feet. Yep, that would probably be better. Thank you. Boom. And then if you know that this is a Pythagorean triplet, awesome. We're going to find out that our A is 12 feet. But that comes from plugging B and C into the Pythagorean theorem. A squared plus B squared equals C squared. And that's going to give us, maybe I'll do that down over here. And do that in section 2. This is going to be our function. A squared plus B squared equals C squared. This will be our equation. Using the word equation because it's not really a function, but same thought process. So that comes from taking the 5 and putting it in here, putting the 13, putting it in here, and solving. Oh, you know what? Yeah, that's over on this computer. Sorry. Yep. Gotcha. And then we've got basically A squared equals 13 squared is 169, 5 squared is 25, and that gives you 144. So A equals 12. Generally, and one of the very first homework questions has a Pythagorean theorem in it. If you were really solving that equation, you should be writing A equals plus or minus 12, but you are not 12 feet below ground, you're 12 feet above ground. All right, so we have our A, B, and C listed out. We had to get one of those values from the original equation that models the situation. We have one more number in our problem, and that's the 2 feet per second. But what are we going to label it? That's what I want to know first. dA dt. Yep. So d little a dt. The rate at which the length of a is changing. And what are we going to say that equals? Are we going to say that it equals 2? Negative 2. Because that length is not increasing, that length is decreasing. And our goal is to find
what rate is the base of the ladder moving from the wall?
Yep, when it's 5 feet from the wall. So what are we trying to find? dB dt. dB dt, yep, equals question mark. That is our goal. Okay. All right. So now we're going to plug in any static variables. That's going to make this a lot easier. We said that c is a static variable. We're going to plug that in and differentiate that. So I'm going to rewrite a squared plus b squared equals, but I'm not going to write c squared. I'm going to write 169 there. And we are ready to differentiate. I guess that's part D. 2a plus 2a dA dt. There's every single differentiation requires a chain rule when you're doing related rates, plus 2b dB dt equals 0. Okay. If you didn't plug your static variable in, you'd have to differentiate the c, and you'd write 2c dc dt. We don't have dc dt listed, do we? But if the ladder's length isn't changing, what's dc dt? 0, right? Yeah, that's the thing. A static variable, the rate of change of it is 0. If it's static, it's not changing. So we would end up with 0 there anyway. We would have 2c dc dt. Then we'd have to say to ourselves, oh, duh, dc dt is just 0. So save yourself the second by doing that. All right, so we're ready to plug in, and we are ready to solve. So we have 2 times 12 times dA dt, which we know is negative 2, plus 2 times 5 times dB dt, which is what we are trying to figure out, equals 0. And we've got negative 48 plus 10 dB dt equals 0. Yep. Bring that 48 over to the other side. Well, that's the question. Bring that 48 over to the other side. You end up with 48 divided by 10. So let's just write that as 4.8. Same label, feet per second. And keep in mind, Franklin jumped and said negative really quickly, but it's not negative. It is positive. As that ladder is falling down the wall, is the length from the base to the wall getting bigger or smaller? Bigger, so that's why it's positive. So if you've done everything right, your sign should always make sense. dB dt is positive because that length from the bottom of the ladder to the wall is getting bigger. dA dt was negative because the length from the top of the ladder to the bottom of the wall was decreasing until it was 0, until the ladder fell down all the way. Questions on that one? You're ready. All right, let's do examples 5 and 6. That will leave us 7 for Wednesday. All right. Examples 5 and 6 really bring the idea of static versus dynamic variable out. Water is being poured into a cylindrical container, so into a cylinder, at a rate of 4 cubic meters per second. The radius of the jar is 3 meters. At what rate is the height of the water changing? There's an extra is in there. When the water is at a height of 10 meters. So let's draw a picture. Cylinder. Radius of the jar is 3 meters. Pretty big jar. Maybe it's a tank. I don't like that. Go back. Big jar, 3-meter jar. It's also 10 meters high. Maybe this should be in centimeters. This is a big jar. This is a 9-foot jar, 9-foot wide jar. Okay. Nope. Yeah. And we've got a water in this jar, and we are concerned about when the water has a height of 10 meters. Cool. All right. What formula are we going to use to help us with this? The cylinder formula.
Oh, it's just circle area.
Yes, like 4
Yep.
pi r squared.
Yeah. Base area times height is what you use for prisms and cylinders. So the area of that base times the height. Most of the times that would be given, but this is lecture, so I can kind of just try to pull it out to you. So it's V equals, because it's the volume, pi r squared times the height. Okay, so that's the formula we're gonna need. We kind of need that in the back of our head. That way we can just label everything with its correct measurements. So let's look at our numbers. What are we gonna label the 3? That should be easy. Yep, r equals 3. What are we gonna label the 10? Yep. Static, dynamic.
8 is dynamic.
And by 8, you mean 3? Wait. Oh, H. I thought you said 8. Sorry. Yeah. Yep. 10 is dynamic. These are meters. This guy is dynamic. And this guy is static. Alrighty. How about the 4? What are we going to label that? Use the label on 4 to help you out with this. 4 cubic meters per second.
Oh, that's
It is. It's a rate, though. Rates we don't.
Oh, we don't classify those.
Yeah, we don't classify those because those are. We're going to plug those into the differentiated version, so it doesn't. We've already differentiated, so it's what? Does V equal 4? It's not V. It's dv dt because it's a rate. It's a derivative. So dv dt equals 4. Okay.
Is it positive?
Is it emptying or increasing? Being poured into. Yeah, I hope my picture. Yep, into. So we have water going into the container for. I think it's good practice to label them. So let me do that. Cool. Yep. All right. Yes, sir. I might if it were an FRQ, they generally don't pull this problem solving part out of an FRQ. So I don't see it. I don't see the scoring guide having that much labeling in it. I don't see the labels being what's perhaps if the answer says label your answer and you don't label your answer, that's what's going to get you. But I know a science teacher would hate how loose I go with these, so keep that in mind as well. All right, so I think we have everything that we need there. We can plug in any static variables, so this should be relatively easy. We end up with differentiating the volume formula, dv dt. Actually, let me rewrite, plugging my static in first. I feel like I'm doing too much. We would end up with v equals pi times 9. So I'm just going to write 9 pi h. Agreed? Statics can go in now. You plug the 9 in, you're good. You plug the 10 in, you're bad. I should say plug the 3 in, you're good. So dv dt equals. It does, but I want to differentiate the formula that I have there. That wasn't what I was asking. 9 pi dh dt, you got it. Oop, changed to the wrong color. 9 pi dh dt. Does the rate of change of the volume depend on the height? No, not in this. Yeah. Nope. I mean, because this is, well, the height might, but the rate of the height is what we're, my question was, does the rate of the volume depend on the rate of the height? That's the key. Sorry, does the rate of the volume depend on the height? I see why you asked that question. Gotcha. Does the rate of the volume changing depend on the height? No. No matter at what height you are in a cylinder, and that's because really the cylinder looks exactly the same no matter where you are in the height. So yeah, no, it's literally the fact that I asked when the water is at a height of 10 meters isn't going to affect this problem. We're actually never going to need to plug 10 into this. So to answer our question, dV dt equals 9 pi dH dt. Oh, we know dV dt, so I'll put a 4 in there. And we want to find dH dt. So dH dt is 4 over 9 pi. Because that cylinder looks the same the whole way up and down, and because the math tells us as so, yep, regardless of what the water height is, if that d, let me get it right, vdt is 4, then dH dt has got to be 4 over 9 pi. All right, let's take a look at the, and the picture should show us this. I don't know if I have this. Let's see if I have it. Yeah, so we're filling it up. I actually have the height increasing at a constant rate in this picture. Is the volume increasing at a constant rate as well? Yeah. Yep. You're increasing the same amount of liquid with each passing second as the height increases the same amount with each passing second. Sure. I mean, yeah. I think 12 is just a number I made up to do this. Yeah. I mean, the question was about 10, so I just made my cylinder go up to 12 because I needed a stopping point. So, yeah. All right. Okay, so there's that question. Now let's do the same thing, but we're going to fill up a cone, or maybe empty a cone. I forget which one it says. Oop, wrong one. All right. Yep, no, we're going to fill up a cone instead of a cylinder. So we have a paper drinking cup that has a height of 6 inches and a radius of 2 inches at the top. How fast is the water level in the cup rising if water is being poured in at a rate of 1 cubic inch per second and the water is 2 inches deep? So we have a cone instead of, that's not too bad, a cylinder. This cone has a radius of 2 inches, which is a lot smaller than our giant cylinder from last question. Unlike the last question where I just had to say, okay, my cylinder's 12, we actually do know the full height of this. It depends on what we're trying to figure out, but we're not trying to figure out surface area, so no. Slant height's a thing, but that's for surface area. But our water level, where we're asking, we are only 2 inches deep of water. So right now, our water level is here. 2 inches. So the one thing about a cone that you would have to know to do this problem from scratch is that no matter where you are in that inside of that cone, the ratio of the overall height, the ratio of the height to the radius will be constant. So that 2:6 ratio, radius to height, that's the same no matter where you are. So if I only had 2 inches of height right there where my water is, that would mean that's 1/3 the height. That means my radius would be 1/3 as well. So that's a piece to these cone problems that you have to know. That is how cones work. If you are within the same cone, that 2:6 ratio will always hold. So if you are 1/3 the height, your radius would also be 1/3, 2/3. Yep. Okay. But yeah, that's the little piece of information you need to know. Let's knock everything else out of this. Let's take a look at the picture though for a second on Desmos, and we'll answer the question if in this one I had to do a little bit more work because the volume is the thing that's constant. If I pour water in at a constant rate, does the height increase at a constant rate? And that should make perfect sense, right? Because I have a whole lot more to fill. So this picture represents me filling the volume at a constant rate. It fills up fast when you're near the bottom because there isn't a whole lot of space to fill up. And it slows down the further and further you go up. So I actually had to go out of my way to actually make the volume constant and back figure out the height. Anyway, I'm something. So where are we at? We are in Flexel still. Okay. Volume formula for a cone. Very similar to the volume formula of a cylinder. Yeah, it is 1/3. So three-dimensional figures, for whatever reason, hold 1/3. When they're a cone, they hold 1/3 the amount of their cylinder counterparts.
That's the first one I wrote on that.
If you had a cone and a cylinder of the same dimensions, same radius at the top, and same height, you could fill the cone up 3 times and it would fill the cylinder. Yep. I know, yeah, no, it's just sometimes things don't have, there might be. Probably has something to do with the derivative somewhere, but off the top of my head, I don't know it. We actually need a second formula for this, and that is going to basically be the one that I talked about, the relationship between the radius and the height. If I know the radius, what do I have to do to get to the height? Multiply by 3. So I can write R equals, I said that wrong, H equals 3R, right? Perfect. All right. Okay, so we have our picture, we have our formulas. I actually think I may switch the order of that in the example because I feel like that's where I go first. Get the formula so then you can label everything correctly. Numbers in our picture. What can we label? R equals 2. Does R equal 2? Where we're at in our problem solving spot? Yeah. It does, yeah. R equals 2/3. Yep. This first sentence isn't actually numbers that we need to use to solve the problem, but this first sentence is related to, this. It basically is the information to write that second equation. It doesn't matter. We'd get the same answer if we had a 12x4 cup, right? It would just be twice as tall. It'd be, it would feel a lot bigger. But to answer this question that they're asking here, it doesn't matter how tall the cup actually is, as long as it's at least 2 inches tall to make the question make sense. But that was some extra information to write that second equation. Yeah, that's a piece of information you need to know about a cone. Something that I don't think you'd ever think about until you hit like these questions. Yep. So we know that R is 2/3. What else do we know? Yeah. What other numbers do we have to label? 1. And what's 1? Again, look at the label. dV dt. It's a volume, right? 1 cubic inch per second. dV dt equals 1. And then our other number is 2 inches deep, a repeat number, but it's definitely a different 2. H. Yep. Are either R or H static? As you're filling water up in that cone, are either R or H static? No, those are both dynamic variables. Do we ever ask that question about dV dt? No, we only care about the actual, the non-rate variables. Those are the ones that are static and dynamic. Okay, so what we're basically going to do here is we are going to, our goal is to find dH dt, right? So we actually want to lose the R in our volume formula. So we're going to take H equals 3R and rewrite that as R equals H over 3. Take our volume formula. 1/3 pi H over 3 squared times H. I think I did need to do this in order to get that Desmos thing working. Like this was problem solving for the problem, and I needed to just get this thing into terms of 2 variables so that Desmos would work. clean that up before we differentiate. Sure feels like 1 over, going to be the denominator there if I combine everything I have. Just the denominator, 1 over what? I got 1/3 times pi times h over 3 squared times h. I'm asking what to write underneath the 1. To simplify. E equals 1 over what? Yes, 27. I've got the 1/3 original, and that h over 3 is giving me 2 more 3's in my denominator. 3 times 3 times 3 is 1/27. Times pi, so let's just write pi over 27 times h to the 3rd power, yep. So now we're set. That's a much easier differentiation than anything else we saw there. dv dt equals 3 pi over 27 h squared dh dt. All right. Plug in 1, 3, simplify 1/9. So we've got, looks like h squared is going to be 4/9 dh dt. Missed a pi there. Yeah. This is our last example. Yep. You too. So dh dt equals 9 over 4 pi. Yep. Same label, not same label, but height is in inches. It's a time rate, so inches per second. Go. All right. Related rates. They're fun. Yeah. That's why I said, like, there's there's 1,000 questions in that book, and there's a pile of different ones that you can, any formula that relates to things, you can write a problem based on it. Shapes, but then you've got, there's one that I cut out that was similar figures. So similar figures they're actually really easy, but the problem is people don't know whether to pick similar figures or Pythagorean theorem, which they really should. So I get disaster on the test when I did both. So, okay, so you guys have 10, 15-ish minutes to work on some of those problems. Go for it. As far as I can tell, I'll steal this one. You guys should be able to do just about everything except for 17. Yeah. Yeah, everything in that packet is doable except for 17. When you get to 10 to 14 on this page, this one shouldn't take you too long. This is really just, I just liked it. It was just good practice at just reading a problem and picking one of the things that you would write as the labels. That's all it is. So it's like, which of these would be one of the things that you would write after reading this problem? That's all you have to do. There's no work to do on 10 to 14 other than read it and pick it out. When you get to the back on 19 through 21, 19 through 21 are the types of questions I was saying that you might see on the AP test. So everything's self-contained. The problem solving is, for the most part, taken out of it. So those are really good problems. But yeah, no, I think everything here, with the exception of 17, because it's just a final example that I want to show you on Wednesday. And then we'll have all of Wednesday to work and anytime after the quiz tomorrow to work. So this is a big packet, but I'll give you some time on it. All right.